All right, so in chapter 3, we're moving into talking about the periodic table and introducing some things that we need to know about the periodic table. We're also looking into elements a little bit more and what elements are, but really we're kind of diving in and getting a little more familiar with the periodic table because that's our main tool that we use to access, knowledge about atoms. And so we got a little introduction in our last segment about atomic mass and atomic number and where those are located on the periodic table and how they help you, how that is found on the periodic table. But now we're going to start looking at some patterns on the periodic table and why it is laid out the way that it is. So we're going to start with, let's review the difference here between atoms, elements, and compounds. So atoms is what we spent the last week or so kind of studying. Atoms are the smallest part of an element that maintains all of the chemical properties of that element. So remember, an atom has to have a certain arrangement of protons, neutrons, and electrons, and that arrangement of those subatomic particles makes the atom behave the way that it does, right? If it has extra electrons, that atom has a negative charge. If it has less electrons, that means that atom has a positive charge. And remembering that atoms have a very set number of protons, which is its atomic number. Okay, so the atom is the smallest part or the smallest unit of an element, but it's important to know that in order to be an atom, it has to maintain the chemical properties of that element. We're not just talking about electrons or protons or neutrons. Those are small parts of an element, but atoms have to maintain the chemical properties. So now let's get into a little bit more of what an element is. We've talked about different elements, right? The elements are all of the things that are found on the periodic table: carbon, nitrogen, oxygen, hydrogen. All of those elements have a spot on the periodic table. But what an element is just a pure substance, and it's only made of one kind of atom. So an element is oxygen or carbon or nitrogen. All of those are found on the periodic table. Once you are looking at an element like carbon or like oxygen, we don't break that down into smaller types of substances, right? If we've got oxygen atoms, we can't break those apart to be two smaller, different types of atoms. Oxygen atoms are oxygen atoms. And if I'm looking at oxygen in particular, I know that an oxygen atom has 8 protons. And if I try to break that down into two different elements that have 4 protons each, well, those are no longer oxygen, right? An atom that has 4 protons is not oxygen anymore. That's a beryllium atom, right? So when we break down elements, we're not making a different type of oxygen atom. We've got a totally different element. Okay, so we don't break down elements into new substances. If we remove electrons, now it's just a different type of element. Okay. So those are some examples of elements. We see all of the ones on the periodic table. Those are all elements. So all 18, 19, however many your periodic table has, that's how many elements we have. Lastly here, we're going to look at something called compounds, and we're going to get to these kind of at the end of the chapter, but I want to introduce them to you first. Compounds are a substance that's made when 2 or more atoms chemically bond together. 2 or more atoms chemically bond. Okay, so that means that if I have a hydrogen bonded to another hydrogen, that makes a molecule or a compound of H2. But if I just have 2 hydrogen atoms hanging out next to each other, not bonded, that does not make a compound. Okay, in order for something to be chemically bonded, there has to be a trading or a sharing of electrons. And we'll go into that a little bit later in this semester, but in order for something to be a compound, we can't just have elements that hang out next to each other. We have to have them chemically bonded. That's an important part of a compound. So water, H2O, is an example of a compound. C6H12O6 is an example of a compound. So chemical compounds have more than one atom. And you might notice here, when I'm talking about a compound like H2O, this right here is called a subscript. Sub means below, so it's a subscript, and this tells me I have 2 hydrogen atoms. And since there's not a subscript right here, we assume that there is a 1 there. So that means I have 2 hydrogen and 1 oxygen atom. Okay, in this next substance right here, C6H12O6, I would have 6 carbon atoms bonded and H12, so 12 hydrogen atoms, and I would have 6 oxygen atoms, all that make up this one big molecule or this one big compound. Okay, we don't need to know a whole lot about compounds yet, but we know that compounds can be made from any 2 atoms that are chemically bonded together. Okay, so let's start now looking at the periodic table and how it kind of came about. Okay, when we're looking at atomic theory, that was in the 1800s and in the early 1900s. So in this time, chemistry is really taking some big steps forward. But in this time, only 60 elements had been discovered. So if you look at your periodic table now, we've got about 117 to 119 elements discovered, and your periodic table might not show all of those. But at that point, there had only been 60 that were discovered. A guy by the name of Dmitri Mendeleev, this is an important name, okay, Dmitri Mendeleev, he developed the first organizational system for the elements. So he essentially discovered, or I guess not discovered, he technically thought up or developed the very first version of the periodic table. Okay, he put these elements that we knew about and their information in an organized system. So he was the first person to really do that. His periodic table listed the elements in columns in order by atomic mass. Then he grouped them by elements that behaved similarly. So I want you to understand that Mendeleev, the very first periodic table, he grouped by atomic mass. When we look at our periodic table today, we know that it really is not going by atomic mass, but it's going by atomic number, right? Hydrogen has an atomic number of 1, helium 2, lithium 3, 4, 5, 6, 7, 8, 9, 10. We're going increasing atomic number. Atomic mass just happens to increase with that. So his periodic table is different than what we have today, okay? But his first one was grouped by atomic mass, and that's important for us to know, okay? Here's kind of a picture of what his first periodic table looked like, or the layout of what it looked like. Here's hydrogen, and then we kind of skip to beryllium, boron, carbon, nitrogen, oxygen, fluorine. Here's lithium over here, right? You'll notice that we're missing some things in between here, specifically helium. We're missing some things between fluorine and sodium. We're missing some different things in this periodic table because, like I said, only 60 were discovered. Okay. I also want you to notice that he's got some question marks in here, right? He had some predictions that he made about elements that were going to be discovered. Okay, so he even left some spots. He left gaps in the periodic table since there were no elements that seemed to fit in those spots, yet he knew, based on the patterns that he had written out, that there should be elements that fit those spots. So he was so smart to not only know how these elements should be grouped, but he also understood that there's probably elements out there we haven't discovered that will fit in the gaps he left in his table. Okay, so he's very, very smart and very, just had a good idea of what was happening with all of these elements and their patterns, but he just didn't have the power to discover all of them yet. Okay, come to find out, those elements were eventually discovered, and they did fit perfectly into the spot that Mendeleev left for it. Okay, so now after Mendeleev is done with his table, another guy by the name of Henry Moseley, he came about and set the periodic table in order of atomic number, so proton number, not atomic mass. That, of course, is how our periodic table is set up today. So he kind of is the father of the modern periodic table, whereas Mendeleev kind of initiated the very, very first periodic table. The reason Moseley set up the periodic table according to atomic number rather than atomic mass was that it made the characteristics of the elements repeat at really regular intervals. So it allowed us to see very specific patterns in the periodic table. And I'm going to show you that in here in just a minute and kind of talk through that with you. But the point of arranging it by atomic number or proton numbers rather than by atomic mass has to deal with having those element characteristics really repeat at regular intervals. So the modern periodic table is arranged by atomic number, like we said, right? Atomic number, not atomic mass. We see a very clear pattern when we look at our periodic table that we increase atomic number. So hydrogen is 1, helium is 2, 3, 4, 5, 6, all the way down, 25, 26, 27, 28, 81, 82, 83, 84, right? It goes all the way to the left, and then you go down a row, and then all the way from left to right, then you go down a row, left to right, then down, left to right, then down, right? They're increasing, and it allows us to see some patterns there. Okay, so our atomic number increases as we go from left to right and from top to bottom. This establishes what is called periodic law. And all periodic law is tells us that when we arrange in order of atomic number, we see repetition of some physical and chemical properties. So the way elements behave becomes very apparent and very obvious. The way that elements interact, that all shows up as a pattern on the periodic table when we follow this rule. All right, so let's look at the periodic table itself. The periodic table is organized into two parts called groups and periods. Groups are the columns on the periodic table. They go up and down. And that is most of the time how we refer to the periodic table. I will tell you to look at group 6 or group 2, and you need to know that groups go up and down on the periodic table. So if I was looking at my periodic table here, right, if I pull that up and I show you a group goes up and down, right? This is a group. This is another group. This is another. All of these are individual groups, okay? I'll talk about what these guys do down here in a minute, but for what we're looking at, the groups go up and down. And you need to know that a group is a column of elements on the periodic table. So it goes up and down. Sometimes your book or your CK12 or whatever, I guess we don't really have a book, but sometimes they will be called families. Groups will also be called families. I very rarely use that term. I more often use the term groups, but you do need to know that those are kind of interchangeable. So if you see something talking about a family of elements, that also will be a up and down column. Okay, these groups on the periodic table have similar chemical properties. Similar chemical properties. And all that means is that elements within a group tend to behave the same. They tend to like to bond with the same things. They tend to react in the same way. They tend to have the same number of valence electrons. They tend to have the same level of reactivity. Okay, they just behave the same or similarly. Maybe not exactly the same, but very similarly. Okay, the other part or the other way that the periodic table is by something called periods, and periods are the rows. They go left to right. So if I pull up my periodic table here again, a period would go across. That would be period 1, period 2, period 3, period 4, right? 5, 6, and 7. Okay. Now, we don't really refer to the periodic table in terms of these periods very often, but we do need to know what they are. Okay? The reason we don't use them very often is because the properties of these chemicals, of these elements, they change as you go from left to right. They change pretty drastically. If I'm looking at, the period that starts with lithium, Li, and goes all the way over to neon, Ne, if I look at that period, lithium, way on the left, behaves way differently than neon on the right. Okay, so if I'm looking at this period right here, although they're in the same period, lithium behaves very, very differently than neon over here in atomic number 10. So we don't really refer to them that often together, but you do kind of need to know what they are like. If they are close together within their row or their period, they do tend to behave similarly. They tend to be more alike, but generally we like to group things in their group, right? In their up and down column. All right, so now that we have a basic idea of how the periodic table is organized, we're going to start getting into some specifics about how the periodic table is organized. We know that in most of the ways we talk about the periodic table, it's going to be via their group, right? We're going to talk about a group of elements. But I want to start with the larger picture first, and then we'll get a little bit more specific here. So the first big area, not necessarily group, not a column, the first area of the periodic table we're going to talk about are the metals. And the metals are by far the most abundant section of the periodic table. A majority of the elements are metals. Okay, and metals have specific properties, things about them. So we're going to really list out some things that we need to know about what makes a metal a metal. Okay, so these are some properties of metals. Generally, they are shiny, right? They've got some shine to them. Think about what you know about typical metals and see if they match these characteristics, okay? So they're very shiny. They are good conductors of heat and electricity. So being a conductor of heat and electricity means that heat and electricity travel well through metals, okay? When you have a metal pan, it heats up and it stays hot for a little while or while heat's on it, and then it might take a little while to cool down, right? Depending on what type of metal it is. But heat travels well through that. Electricity travels through metal. That's why we use metal wiring, right? We want that to travel well through there. So they're good conductors. That means it travels through. Most of them are solid at room temperature, okay? Most of them are solid in general, but you might even want to add on here that we're talking about at room temperature. Most are solid. An exception to that, maybe the only exception to that, is mercury. And mercury is a liquid at room temperature. Most are what we call malleable. This might be a new word for us. Malleable means it can be flattened into thin sheets. So I want you to think about what are some examples of metals on the periodic table that might be considered really malleable. What are things we know that are really malleable? For example, aluminum, right? We use aluminum foil. Tin is abbreviated SN. It's atomic number 50 if you want to look at it. Tin is what we make, tin cans from, things like that. Gold is AU. That's can be put into a really thin foil. Same with silver, AG. Right, we've got a lot of very typical metals here that we know can be flattened into these tiny or thin kind of sheets and then become very pliable. So that's what malleable means. We can flatten it out, we can mold it, we can kind of manipulate it into a thin sheet. Most metals are what we consider ductile. Ductile is also probably a new word for us. It means that it can be drawn or pulled into a thin wire. So there's probably at least one example that's really coming to your mind here about a ductile metal, and that would be copper. Copper is abbreviated Cu. Okay. Copper is a good one. There's just really a lot that can be considered really ductile metals. Lead, right? We use lead to draw and make pipes, things like that. Lead is Pb. Right? But there's a lot of different examples of really ductile metals. Those are two new words for us, so please make sure you have an idea of what those mean. Metals also tend to have high tensile strength, and that just means they won't shatter easily. Okay, so it's almost being like the opposite of brittle, right? They won't shatter easily, which means if I were to hit it, with a hammer or, drop it on the ground, it's not going to break into 1,000 pieces. It's not brittle, right? Metal, when I drop it, it's probably going to hold its shape. There are some metals that are real soft, but for the most part, when we think about metals, we're thinking about ones that really do have a pretty high tensile strength. Okay, so here's an example first of a really soft metal. These are metals that are kind of found on the far left of the periodic table, like lithium, sodium, potassium, rubidium. All of those metals, way on the very far left, they're considered really soft metals. So they are ones that they're not going to shatter when you drop them, but they might make a dent, right? They're not really hard. This is a metal that has an extreme shine to it. Usually we don't even see them that shiny, but that's pretty extreme. This is an example of ductility, right? We drew that copper into a really thin wire, and then we also see electricity traveling through that wire and really heating it up. And then last, we've got an example of kind of a more brittle metal. You see how it kind of makes a, makes almost little like shavings or something. You can tell if you dropped those, they might shatter a little bit more. Those would be some metals over kind of on the extreme side, so on the far left and then a little bit closer to the right-hand side. Okay, so those were metals. I'm going to show you in a second what area of the periodic table those metals fall on. But now let's switch to the opposite side of that. Non-metals are basically the exact opposite of metals. They basically behave exactly the opposite. They are mostly gases at room temperature. So guess what types of elements might be considered nonmetals? Things like oxygen, nitrogen, fluorine, chlorine, right? All of these might be gases at room temperature. If, however, they are solid at room temperature, they tend to shatter very easily. So they are very brittle. Okay? If they are ones that are solid at room temp, they tend to be very, very brittle. So these are things like sulfur, carbon, phosphorus, iodine. Those are all examples of ones that are solid at room temp and they end up shattering. Nonmetals are really bad at conducting heat and electricity. They don't travel well through there. That's good for us, right? We breathe in oxygen. We don't want electricity traveling through our oxygen and into our bodies, right? That would be a big problem. So we're glad that nonmetals do not conduct heat and electricity. Okay, so that's about it for the nonmetals, right? It's a smaller section of the periodic table, but they essentially behave opposite of metals. The last little area of the periodic table I want to speak to is something called metalloids. Metalloids. And metalloids, in its most basic definition, have some characteristics of metals and some characteristics of nonmetals. There's not very many elements that are considered metalloids. Okay? They are typically solid at room temperature, so that's similar to a metal, right? In that they're solid at room temperature. They are less malleable than true metals, but they're not as brittle as nonmetals. So they kind of fit somewhere in between there. Some of them have a very metallic shine, so some of them are very shiny. Antimony is an example of that. Antimony is element Sb, atomic number 51. So you can look at where that's located on the periodic table. And they are what we call semiconductors of heat and electricity. So that means heat can travel and electricity can travel through there, but it's not done as easily as in a true metal. Okay, so you've got metals on one side, non-metals on the other, and metalloids that fit right in the middle. Okay, so there's an example of really shiny antimony. Again, they're really, really shiny. And then silicon is a big metalloid for us, and it's really, really frequently used in microchips and things like that. So that's an example of where it's a really good conductor, even though it's considered a metalloid. So here is an example of where the metals, nonmetals, and metalloids fit on the periodic table. And so I want you, if you would like, you don't have to do this. If you want your periodic table to stay nice and white and clean, you can. But if you want to, you could grab 3 different colors of colored pencils and shade your periodic table in the way that this one is shaded. Okay, in that all the reds are metals, so you can pick whatever color you want for metals, whatever color you want for metalloids, and whatever color you want for nonmetals, and shade your periodic table like that. A couple things I want you to pay attention to is that hydrogen, although it's over here with the metals, it's still a non-metal. Okay, it only sits over there because of the number of electrons it has. I also want you, regardless of if you decide to shade your periodic table or not, I want you to draw in this thickened line right here that I'm going over right now. That line I call the stair step. You'll hear me talk about the stair step. That line right there, and I'll get rid of my line, but that blackened line that walks down from here to here, that is called the stair step, and that gives us really kind of a very true separation of metals and nonmetals, right? Metals are on the left side of the periodic table. Non-metals are typically on the right side of the periodic table, but you've got these metalloids, the yellow guys, that surround that stair step. So I want you to take some time now, before you get started on the homework, to either shade your periodic table. You probably have to pause the video right here so you can see where it needs to be shaded at. But I for sure want you to draw that stair step, right, where I'm drawing it there. That needs to go on your periodic table for sure. And then if you want to shade them in the 3 colors, you can do that as well. Just make sure that you can still see all the numbers on your periodic table. You still need to be able to see the atomic number, atomic mass, all that kind of stuff. So that's where we're going to stop for today. If you want to go ahead and shade that periodic table, you can do so. If you want to just draw the stair step, that's fine too. But please get that done before you start on the homework.